Um, Hi everyone. The idea of this project is to use randomized sampling technique to construct approximate Cholesky factorization as the preconditioner for solving linear systems. In particular, we consider solving STD linear systems. So here, the definition of STD we use is that first of all, A is symmetric, and the diagonal element is larger or equal than the sum of the absolute value of the rest of entries in the same row. Notice that we do restrict ourselves to have non-negative diagonals. So furthermore, we assume the matrix A is non-singular, and also A is irreducible. By being irreducible, that means the original problem cannot be decomposed into two or more independent subproblems. Now, this type of linear systems arises very frequently in many applications. And in particular, we consider those as the discretization of PDE's file, finite element or finite difference methods. Now, our work has mainly 4 parts, but due to the time limit, I'll focus on talking about the randomized Cholesky factorization for Laplacian matrices, which is a subclass of STD matrices. And I'll present numerical results of the overall approach. Now, first of all, the definition of a Laplacian matrix is that L is a symmetric matrix and non-zeros in the off-diagonal are all negative, and every row and column sum up to 0. It's easy to verify L is an STD matrix in this case. And more importantly, notice L is actually singular. And the null space, it's easy to verify that the constant vectors are in the null space. And if we assume L is irreducible, then the kernel null space is exactly the one-dimensional space spanned by constant vectors. Now, in this talk, it's important to mention that L actually maps to a weighted undirected graph. So for matrix L, we can construct a graph with n vertices from 1 to n. And a vertex edge exists between vertex I and j if there's a non-zero off-diagonal entry. And the weight associated with that edge will be minus Lij. Okay. Now, before introducing the new algorithm, let me first review the classical Cholesky factorization to establish the background. The input is an irreducible Laplacian matrix, and output will be a lower triangular matrix. Now, as I mentioned, L is singular, so we can't apply Cholesky from step 1 to step n as usual. Instead, we prove that it's easy to prove that the diagonal entries are positive for the first n minus 1 steps, and then you will get a 0 at the bottom right. Now, it is here I mainly used for this talk. I mainly use MATLAB notations. So this should be the familiar rank 1 update in the Cholesky factorization, where this is the kth column and this is the kth row. It is well known that the elimination leads to a dense update in the Schur complement. Now, let me give you an example shown in this figure where L is a 5 by 5 matrix. It's showing in figure A, where L is a 5 by 5 matrix, and the figure shows the graph of the matrix. Now, if we eliminate the first vertex, the resulting graph will look like what is a complete graph among the neighbors of A, as shown in this figure. These are well-known results. Now, let me rewrite the algorithm in a slightly different form. I'll write the rank 1 update in 2 terms. Now, the first term is removing the vertex and the edges in the original graph. And then the second component is adding the edges in this clique. Now, the idea of our new algorithm is that instead of keeping the exact clique, we sample a sparse subset of the edges in the clique. So now let me go to the next slide. And this is what we call randomized Cholesky algorithm, RCHOL. Now, the only change from the previous algorithm is this term, the sample clique term, instead of keeping the exact clique. So the figure C shows an example where we sample a subset of the edges. Now, one question we do want to still preserve the property that the diagonal entries are positive, so we can still do the factorization from step 1 to step n-1, and I'll show you a theorem on that. But let me first talk about the sampling algorithm, how the sampling is done exactly. So first of all, we sort all the neighbors. I'll skip some technical details, but instead focus on the high-level ideas here. So first step is to sort the neighbors of the illuminated vertex in some way. And then we loop over all the neighbors. So as you can see in this figure, the red vertex goes over the neighbors. And at every step, we will sample another vertex from the remaining neighbors. So the blue vertex denotes the sampled vertex. And once we have red and blue, we just select this edge between red and blue and assign a proper weight to this edge. And then we remove red if we after sample one edge. Now this figure shows you how we get the final result of this sparse clique. It has 3 steps. Now, even though I haven't talked about the details, some technical details, but with what I have presented, we can already prove that the sampled edges will form a spanning tree on the clique. And the important consequence of that is the randomized Cholesky algorithm. It satisfies what I just mentioned. The diagonal entries are positive from step 1 to step n as well. This is exactly how we designed the sampling algorithm. Now, next, the theorem is about the running time and storage. Now, suppose we pick a random vertex to eliminate at every step in the approximate Cholesky factorization. We can prove that in expectation, the running time and the number of non-zeros in the resulting factorization is going to be n log n, where n is the number of non-zeros and n is the matrix size. Now you may ask the question, what is the approximation error? I haven't presented the details, but I just want to mention that the sampling algorithm is designed to return an unbiased estimator, meaning that at every step in the approximated factorization, the computed result equals the exact factorization in expectation. But of course, the most important thing is how does these errors accumulate after n-1 steps? And for that, I'll show you some numerical results which give evidence that the errors are actually well bounded and depends very weakly on the matrix size. Now, before going to the results, let me just remind everyone that the question we consider here is solving a linear system with using PCG, and our method construct a preconditioner, and I'll call our method RCHOL. Now, some notations, the matrix size, number of iterations, and more importantly, the filling ratio, defined as the number of non-zeros in the preconditioner divided by the number of non-zeros in the original matrix. So this measures the relative storage of our preconditioner compared to the original sparse matrix. Now, in some cases, I'll also compare our method to the incomplete Cholesky factorization with job tolerance implemented in MATLAB. I'll call it RCHOL. Now, the first experiment shows you the performance of RCHOL with using different elimination ordering. As in sparse direct solvers, using elimination or filling reducing ordering affects the performance of the resulting algorithm. So now this table shows different rows are the different type of reordering algorithms. And the different columns shows you, for example, the performance statistics like the storage, the time to compute the ordering, and apply the ordering, and factorization time and the solve time, PCG time. So in general, our observation is that AMD tends to be a good choice, default choice. It leads to a small memory footprint. It doesn't take too much time to compute, and it generally leads to fast factorization and solve time. So we use AMD as a default option, a reordering option in RCHOL. Now, the next experiment shows you, it's very simple. We just run the randomized algorithm multiple times. Now, this is to convince you that it actually behaves like a deterministic method. So in this table, different rows corresponds to different trials of RCHOL for solving the same problem. As you can see, the storage, everything is almost doesn't change very much. Okay. The next experiment shows you how RCHOL scales, the number of PCG iteration scales when you increase the problem size. So this is a simple model problem Poisson equation in a cube, discretized on regular grids. And as you can see, the problem size increases from 1 million to 1 billion. And the number of iterations of RCHOL increases very slightly from 50 to 75. So it looks like the increase is like a logarithmic with respect to the problem size. And if you, by contrast, if you run incomplete Cholesky, the number of iterations will increase much more rapidly. Now, the next experiment shows you the comparison between incomplete Cholesky and our method for solving matrices from supersparse collections. So here are 4 matrices with all with millions of non-zeros. If you when we use a pure CG without any preconditioner, it took more than 2,500 iterations before without conversion. And now the way we compare incomplete Cholesky with our method is that we manually tune the drop tolerance. So the filling in incomplete Cholesky is actually slightly larger than the filling in our method. But you can see that the number of iterations obtained with RCHOL is much smaller than incomplete Cholesky in this case. Okay. Now the last experiment shows you the parallel scalability of RCHOL. I haven't talked about the parallel algorithm, but I just want to show you some results, which is to solve, again, this is solving a model problem, Poisson equation in a cube on regular grids. The problem is 1 billion. And the rows P here is the number of threads used or the number of cores. P goes from 1 to 64. And as you can see, the storage, excuse me, the storage, the first column and the third column is the number of iterations. They are very stable with a different number of threads. Now the second column is the factorization time in seconds. And in particular, on 64 cores, the factorization took a little bit more than 3 minutes. Each core corresponds to 14x speed up using 64 cores. We did this experiment in single precision because our factorization is not exact. And the resulting factorization preconditioner took 130 gigabytes of memory. Consider the original sparse matrix took about 30 gigabytes of memory already. Now let me conclude by saying that our code is open source online. It's on GitHub. It has the C++, MATLAB, Python interfaces, and our preprint is on archive. It has more details. Everything I said can be are made precisely in our manuscript, and it has more results. With that, thank you for your attention, and I'm happy to take questions.
Well, thank you, Chao. That's very kind. Thank you very much for a very nice, clear talk. I should encourage everybody to ask questions, and please ask questions through the YouTube chat during the talks, because if you ask them all at the end, it's very slow for those questions to get through to the chairman to ask. So please do go ahead and ask questions during the talks. Okay, so we have a first question here on YouTube. This is from Alex Pothen. Do you understand why nested dissection ordering takes more time than AMD ordering? Asked Alex.
Oh, this is we compute these orderings with MATLAB commands. So this is I actually don't know how MATLAB implements nested dissection, but it seems it takes a lot of time in MATLAB. But otherwise, nested dissection just performs pretty well in terms of, for example, the memory and factorization time and solve time. And we would be happy to use a fast algorithm to compute nested dissection.
Okay, so there's another question here from Joshua Fogg. You briefly mentioned the parallelization of the algorithm. Is it just the sampling which is done in parallel, or are other parts of the algorithm in parallel too?
No, it's not the sampling done in parallel. It's the overall framework. It's if you're familiar with nested dissection multifrontal, this is pretty much the same framework. We use nested dissection ordering for a couple of levels, in which we decouple the problem into independent dependent subproblems in parallel. So that's pretty much nested dissection multifrontal.
Okay. There's another question here from Bora Ucha, who asks, do you sample according to the weights?
Yes, definitely. It's very important. Let me just go back to this. So first of all, we sort the neighbors. We need to consider the weights, and also the sampling among the rest of the neighbors. The sampling distribution is particularly designed for based on the weights. And also there's another component, which is we do assign a new weight to the selected edge. So this is not like, for example, incomplete. I'll say some incomplete Cholesky factorization method where you just keep the exact entry as it is. Instead, we actually adjust the weights a little bit in order to make the sampling unbiased estimator.
Okay. So can I ask a question then? Which I mean, these look very interesting ideas, and I was wondering what is the primary difficulty in extending what you have done beyond the graph Laplacian matrices. I mean, suppose
exactly.
This is a really, I mean, so for example, suppose that I had a non-symmetric matrix, but it was still had row sums of 0 and positive diagonals and negative off diagonals.
As far as we know, I mean, this sampling algorithm relies on this graph interpretation of Laplacian matrices. So it's not very obvious how to extend that into non-symmetric matrices. We have to consider directed graph, but it's not clear how to do that in a straightforward manner.
So what happens? Are there other ways you can push it? Can you push it the definiteness? I mean, or the diagonal dominance? You could still keep the undirected graph as long as it was symmetric, I guess.
Yes, but we actually do use this property that the off diagonals are negative in this in the sampling algorithm. So
I should say that I just noticed a question from Eric Bowman, which is essentially exactly the same. Is there any hope to extend beyond STD? So we're all interested.
Eric Bowman, he proved a nice theorem in an early publication that you can extend the current approach to some SPD matrices. But I'm not sure I know any other way to extend that beyond that scope. So
well, thank you very much. I feel it's a great pity at the end of these really nice talks that when we're usually in Toulouse, we're able to sit and clap and express our appreciation, and it's harder on this occasion. But thank you very much, Chao, for a very nice talk.